Howdy, welcome to Math 153, Elementary Statistics. I am Lance Curtis. This is the lecture for sections 10.1 and 10.2. As you can see here in Chapter 10, we're going to be talking about correlation and regression. This is where we're going to start making statistical models that can actually make predictions about the future based on relationships between two or more variables. So here in the first section, let's review what we've already covered. In Chapter 9, we looked at models for making inferences from two samples. We also learned that good experimental design favors using dependent samples. So the value from one sample is going to be somehow paired with a value from another sample. We're going to take this concept of paired sample data, but we're going to examine the concept from a fundamentally different perspective because we have a different objective in mind. What that objective in mind is determining the relationship between the two variables. Okay, so there's some association between the variables that exists, and that is looking for that relationship is all the business of correlation. Regression is then where we're saying, okay, how can we represent that relationship mathematically with some sort of line or equation? So we're going to start out by looking at linear correlations and linear regression because in the world of mathematical equations, linear equations are the simplest. So we're going to start with simple linear correlations. Now, when we're dealing with linear correlations, we can identify an equation that best fits the data and then use that equation to make predictions on the value of one of the variables given the value of the other one. And this is where statistics becomes really, really powerful. We're also going to look at some methods for analyzing differences between predicted values and actual values and consider methods for identifying linear equations for correlations among three or more variables. Because let's face it, sometimes you're looking at two variables, but the real relationship you're looking for involves three variables or four variables or five variables. The real world isn't always neat and cut. We're also going to look at developing mathematical models for describing nonlinear correlations. There are many examples in the real world where life is just not linear. And so we need ways to model these phenomena as well. And we have them. And we'll get into that towards the end of the chapter. So with all that understood now, we're going to go into the next section and learn about basics of correlation. Remember, correlation is simply looking for relationships, okay, associations between two variables. So we measure this, the strength of this association or relationship with a linear correlation coefficient, R. Now, the author of your textbook uses a lowercase letter r. This is not very common. In the real world, based on my experience, what I've seen is a capital letter R. Regardless of which one you use, it's measuring the same thing, okay? The strength of the relationship between the two variables you're examining. Now, we're going to be using paired sample data, okay? Sometimes this is called bivariate data. Bi is a prefix from the Greek meaning two, and variate is another form of the word variable. So we're looking at two variables, hence the term bivariate. This is a good expression for paired sample data. We can find the value of R, and usually we're going to use software to do this. We'll get into how to calculate this old school later on in the lecture. And you'll see that this calculation is just a monstrosity, so we're going to be using the software for it. And then based on that calculation, we can make a conclusion regarding whether or not a linear correlation exists between our two variables we're examining. Now, we're only going to look at linear relationships in this first section on correlation. Okay, what that means is that when you graph the relationship, the data points will approximate a straight line pattern. So, as I mentioned before, okay, life isn't always linear. There are many examples in the real world that have a nonlinear relationship, and we're going to look at those later on in the chapter. But for the purposes of this lecture, we're going to confine most of our attention to looking at linear relationships. And of course, we're also going to look at hypothesis testing. Can't get away from that. We can actually use hypothesis testing to evaluate correlation. To start off with, let's look at some definitions. So, as I mentioned previously, a correlation simply means that you've got two variables and they're somehow associated with each other. There's some relationship between them. Okay, so for example, looking in the graphic, we know that auto value and auto mileage are related. The more mileage you have on your car, the less it's typically worth. This is what we would call a negative correlation, because a decrease in one variable increases the other variable. An increase in one variable represents a decrease in the other variable. Then we have a case where we have no correlation. So for example, auto quality and auto body color. Well, the quality of the car you buy has no relationship with the color of the car. So these two variables are not correlated. They have zero correlation. And then finally, over on the right, you see auto accidents and auto insurance costs. It makes sense that the more accidents you have with your car, the more your insurance is going to cost. So this is what we call positive correlation. An increase in one variable is associated with an increase in the other variable. And likewise, a decrease in one variable is associated with a decrease in the other variable. Now, this is what we call linear correlation. And what that means is that you're looking at your two variables and there's a correlation between them. And when you plot the points on a scatter plot or graph, the data points will approximate a straight line. Of course, if they don't approximate a straight line, then what you have is what's called a nonlinear correlation, assuming that you have correlation to begin with. If you don't have any correlation, then it doesn't matter whether you're looking at linear or nonlinear, because you have no correlation. But there are many things in the real world that are correlated non-linearly. Okay, so the pattern that the points make is something other than a straight line. So for example, if you take the distance that a cannonball travels after it's fired from a cannon, and you compare that with the height above the ground, you'll see that the data points make a sort of parabola shape. And so you have nonlinear correlation between the height of the projectile and the distance the projectile travels. Sinusoidal curves are used to model all sorts of different things. So, for example, if you're looking at alternating current in the field of electricity, then you're going to be modeling the amount of the current that's traveling through your circuit with a sinusoidal curve. So there's a relationship between current and time, and it's modeled with a sinusoidal curve. Exponential functions are used, for example, to model radioactive decay. So if you have a radioactive isotope and you're wanting to measure half-life, half-life is the time it takes for half of your substance to decay. So there's a relationship between the amount of substance that you have and the time. And that relationship is best expressed with an exponential function. So the correlation there is nonlinear. Now, when we're looking at linear correlation, there is what's called a linear correlation coefficient. Okay, again, your author's using the lowercase letter r. My experience in the real world is that a capital letter R is used, but regardless of which one you're using, it's the same thing. It's measuring the strength of the linear relationship between the paired values in a sample. There are certain requirements that paired data sets must meet in order to be linearly correlated. So the first is your paired sample data has to be a simple random sample, and it must be composed of quantitative data. So if there's any qualitative data or categorical data, this isn't going to work. Okay, you've got to have quantitative data from a simple random sample. Second, the scatter plot is made and it shows the points approximating a straight line pattern. So remember back in chapter 2, I know it was all those eons ago, right? Back in chapter 2, we were talking about graphs, and we mentioned that one of the first graphs you're going to make is a scatter plot. That holds true when you're looking for relationships between variables. One of the first things you're going to do is make a scatter plot. See where the data lie. Oftentimes, if there is a relationship between the variables, especially if that relationship is a strong one, it will show up on the scatter plot. So the scatter plot can actually help guide us. Do we have a linear relationship between the variables? Is the relationship nonlinear? The scatter plot oftentimes can answer those questions. The third requirement is that outliers that are known to be errors must be removed. Now notice I put errors in quotation marks because just because an outlier exists doesn't mean it's something that should be thrown out. Sometimes the outlier actually belongs in the data set. I can't tell you how many meetings I had with other engineers and people in industry when I was working in industry. I mean, we would have all these different discussions, and the meetings would revolve around the data. And I can't tell you how many meetings we had where we had just hour, 2 hour long discussions about these 2 or 3 data points in our data set. They were outliers. Do we include them in the model? Do we not include them in the model? Outliers can be a big deal. And the reason for that is that including an outlier can have a huge effect both in determining correlation and creating regression models. That's because your linear correlation coefficient R is very sensitive to outliers, as we'll get to in a moment. So often what happens is we'll calculate the value of our linear correlation coefficient with and without the outliers in question. If there's a huge swing, then that means we need to make a decision as to whether we're going to leave them in or take them out. And oftentimes in that case, the decision comes that we're just going to take them out. If, however, there is no wild swing, the R values you get are not significantly different from each other, then what you're going to look at is essentially you just basically leave it alone because it doesn't make much difference if you leave them in or take them out. Scatter plots. Now, we just mentioned this. Okay, oftentimes we can see a relationship between 2 variables by constructing a scatter plot. And there are many different ways that the scatter plot can come out. So here we're looking at 6 different examples of how our scatter plot can turn out. Now, the way that we actually read the scatter plot is you want to read it like you would a book. So go from left to right and see if there's any trending in the data as you go from left to right. So looking at the first example there on the upper left, strong positive correlation. Notice how if we read from left to right, it looks like we have a continual steady increase in the data. That's a trending that we're looking at. Okay. Now, if you imagine drawing a line of best fit through your data points, we'll get more in detail with this line of best fit in the next lecture. But for now, just imagine, say, what if we could draw a line that best fit the data, what would it look like? So imagine for that first case, strong positive correlation, we have a line that looks something like this. Okay? So notice how the line is shaped so that it describes the trend of the data. So the line is increasing as we go from left to right. Notice also how the data points are closely adhering to the line. Okay, this is what we mean when we say there's a strong correlation between our 2 variables. Okay, when we graph them on the scatter plot, the data points lie fairly close to the line, so they're really hugging that line. They're loving each other with hugging. Okay, they're hugging each other to death. Moderate or weak correlation is represented. We still have that same trending. Okay, from left to right, we still have a continual increase, but we're looking at data points that aren't so close to the line. So there's more of a spread with the data from that line of best fit. Okay, now we say that in each of those 2 cases that you're looking there at the top, where we've drawn a line of best fit, the line has positive slope. So we say that the correlation between the 2 variables is positive, because that line of best fit has a positive slope. An increase in one variable is associated with an increase in the other variable. A decrease in one variable is associated with a decrease in the other variable. Of course, if we flip that around, we can also have negative correlation. That just means that our line of best fit has a negative slope. So a decrease in one variable represents an increase in the other, and an increase in one variable represents a decrease in the other. Of course, not all variables you have are correlated with each other. So sometimes you get a graph that looks similar to the graph that you see up in the upper right. No correlation means that there's no single line of best fit for the data. Okay? It has a characteristic what I like to call shotgun appearance, because it looks like someone took their shotgun and blew some holes in the wall. And then, of course, as we mentioned previously, real-world examples are often non-linearly related. So you could have a curvilinear or a non-linear relationship between your two variables. Again, this is one of the reasons why we make a scatter plot first thing out of the box, because a scatter plot can tell us so much about what it is we can expect to see from our statistical tests. I mentioned earlier about the calculation for our linear correlation coefficient R, and here it is. You see it right there in the center of your screen. Look at this monstrosity. I mean, imagine, it's like we had, back in the days when I was in school, we had to do this old school calculation. Holy hell, we had Excel, and that made it a little easier, but still, it was an atrocious calculation, and then Microsoft got, really wise and actually put this functionality into their spreadsheet program, as did a lot of other spreadsheet program makers. So that helped. We're actually going to be using software. So in StatCrunch, there is a way for this to calculate automatically. But it's helpful to know how to calculate R, because this leads us to some of the properties that R has. And knowing what those properties are can be very useful. So let's get in a better understanding of the different pieces of this equation. First, notice that we have n. N is the number of pairs in your sample data. Okay, so whereas n has previously been sample size, it's still in a way sample size. It's just that because your data is paired, each of your samples, your x and your y, is going to have the same sample size. So that's exactly what n is. This next term here is sigma xy. What that means is that you take all your x variables and multiply by the corresponding y variables, and then you take those products, you add them together. That's sigma xy. Sigma x means you take all your x variables and add them together. Likewise, sigma y means you're taking all the y variables and adding them together. Sigma x squared means you square each of your x values, and then you add all those products together. Sigma x quantity squared means you're adding all your x values and then you square that sum at the end. That's the quantity sigma x squared, or more accurately said, sigma x quantity squared, so that there's no confusion as to what's actually going on with the calculation. Then we have sigma y squared, which similarly to its x complement, means that you square each y value and then add those numbers together. And then there's sigma y squared, which is taking all the y values, adding them together, and then squaring that quantity. So sigma y quantity squared is the more appropriate way to say this. Now look at the way that this calculation actually runs. Okay. One of the things we notice from this calculation is that you can actually switch the x and y variables, and you're going to get the same number out for R. Okay, so if I switch my x and y variables, instead of taking x and multiply by y, I take y and multiply by x. Okay, well, 1 times 2 is the same as 2 times 1. This is the commutative property of multiplication. It doesn't matter what order you put them in, you're going to get the same product out at the end. So I can switch my x and y variables and still come out with the same R. So if I switch the x and y here, I'm going to get the same number out. Switching the x and the y here, well, I'm just taking this sum and this sum and swapping the order, so that doesn't change anything. And then down here at the bottom of my fraction in the denominator, what's under this radical, this square root sign, and this square root sign, if I just switch the x and y's, then instead of taking the first times the second, I'm taking the second times the first. Again, 1 times 2, 2 times 1, doesn't matter. So I can switch my x and y variables, and I'm going to get the same r value that comes out. So it doesn't matter what I choose to be x and what I choose to be y. The other thing that's interesting to know about this equation is that you're going to get a range of values for what r can be. So looking at this equation, and you think about, okay, so how could this actually come out with my square root signs on the bottom and with the difference that I'm subtracting there on the top? You're not going to get a number for r that's less than the -1, and you're not going to get a number for r that's greater than 1. So it's going to be bounded by that region. So these are some of the properties that we see from r, from our actual equation, and these properties are very useful when we're evaluating r. So as we just previously mentioned, okay, the value of r cannot be greater than 1 or less than -1. So it's bounded by -1 and 1. This gives us a sort of range of values at which we get r. So if you actually are calculating r old school, or you see a number in your software and it comes out and it's outside this range, then you know something's wrong. Okay, it can't be outside this range. If we convert all the values of either variable to a different scale, so let's say we do a data transformation. I'm going to take a log of all of my x values and get a log normal transformation. So it doesn't affect the value of r. Okay. We also see that it doesn't matter what variable you choose to be your x and what you choose to be your y. So I can interchange all day and night between x and y. I'm going to get the same value of r out. The value of r, as defined, measures the strength of a linear relationship. It has to do with this scale that we see, okay, bounded between -1 and 1. So here in the graphic up at the top of the screen, we see some relative r values correlated with some qualitative descriptions of the r value. So if r is 0, we're smack dab in the middle of our range. There's no correlation between our variables. If r is 1, here on one extreme of our range, we have perfect positive correlation. Likewise, on the other extreme, -1 represents perfect negative correlation. Notice that if r is negative, that means we have negative correlation. So the slope of our line of best fit is going to be negative. Likewise, if r is positive, we have a positive line of best fit, positive correlation. Notice that the closer our r value gets to 1, the closer our data points approximate that straight line pattern. The further away it gets from 1 and the closer it gets to 0, the more scattered and less like that straight line pattern we see. Again, on the flip side of our range, notice that the closer we get to -1, the more the data points conform to that straight line pattern. The closer we get to 0, the less likely it is, the more spread out and randomized they are. So the value of r is a measure of the strength of a linear relationship. The closer we are to the extremes of the range, the more likely that our data points are going to conform to that straight line. Because of the way that we calculate r, it's very sensitive to outliers. And so this gets into what I was mentioning earlier, that when you're looking at data points with your scatter plot, okay, looking at those outliers, sometimes you can have some really harebrained discussions about whether or not you include them or not. But once you have all that settled out, there comes the time you need to interpret the value of r. Okay, so the values that you were seeing before in the graphic are merely guidelines. The -1 and 0 are pretty set in stone. You can look at those as rules. But the other values, it's kind of a relative thing. So how do we determine whether or not an r value is strong enough to indicate that our variables have linear correlation? Well, this is where we get the critical r value table that you see there on the right. This is one of the things that we can use to actually determine and answer that question. This table is also included in the insert for your textbook, okay? Table A6. So let me show you how to use this table. First of all, you're going to look at the absolute value of R, and if it exceeds the corresponding value listed in the table, then you have linear correlation. If it's equal to or less than the value listed in the table, then you don't have enough evidence to support concluding a linear correlation. Alternatively, you can use a p-value with a significance level, just as we've done before with hypothesis testing. So if your p-value is less than or equal to your significance level, then you're inside the critical region, so to speak. Conclude you have a linear correlation. Otherwise, if it's greater than the significance level, conclude you don't have enough evidence to support the conclusion of a linear correlation. Please understand that these methodologies apply to linear correlation. So don't go try using this table with an R value that comes from a nonlinear relationship. You can calculate R values for nonlinear relationship. Obviously, the equation for calculating it is going to be different, but looking at this table applies only to linear correlation. So don't try to use it for non-linear relationship. Also, keep in mind that if the interpretation of R comes out to where you don't have a linear correlation, then all that really means is that there may be some other relationship that you need to look for. So if the linear doesn't come through for you, switch to nonlinear. And we'll get to the nonlinear cases later on in this chapter. Let's look at an example to illustrate what we've just discussed. So the table below is listing shoe print length and height, both of which are in centimeters, for 10 male adults. So the questions we're asked is, what is the value of the correlation coefficient R? And then, are shoe print length and height linearly correlated at the 5% significance level? So here's our data. It's paired. You can see this. Before we go into actually looking at answering these questions, let's actually check to see if our requirements are met. So the first requirement is that the sample of paired XY data is a simple random sample of quantitative data. So yes, we have a simple random sample, and there's no categorical data, there's no qualitative data in our data set. It's all numerical continuous data. That makes it quantitative. Second, a scatter plot shows the data points approximate a straight line pattern. Here's a scatter plot of our data, and while it's not exactly a straight line, you do see a general trend as you go from left to right, reading the graph, that there's a sort of a continual increase in the general trend of the data. So if you were to look at, say, bands for the data. So let's look at bands for the data. So we've got the data existing between these two bands represented by the dashed lines. So kind of in the middle of that band would be our line of best fit. And it looks like, you know, the data points are generally following the trend outlined by that straight line. Now, because this band is a little wide and not all of our data points are hugging that line, this could indicate a moderate linear correlation. That will be revealed as we actually calculate R later on. But first we have to check our last requirement. Outliers known to be errors must be removed. And looking at the scatter plot of our data set, everything's more or less together. There are no real outliers for our data set. So therefore, we can now conclude that all of our requirements are met. So now we're actually going to use the actual software. So we're going to stack crunch to calculate our R value. And when we do, we find that R is actually 0.847. How we get that is in Stack Crunch. Here's the results window that comes out when you do the calculation. And notice that the R value is listed up here near the top. Notice also that Stack Crunch uses the more common convention of using a capital letter R to represent the linear correlation coefficient. We can determine whether a linear correlation exists with our critical R value table. So here once again is our critical R value table. We are testing at the 5% significance level, so alpha is 0.05. And then from the table, we notice our critical value is 0.632. How do we get that? Well, remember we had 10 pairs of data, so n is equal to 10. Alpha is equal to 0.05, so we want the value in the first column. That's going to be right here, 0.632. That's our critical value. So now we compare the R value with this critical value, and because 0.847, which was our R value, is greater than this critical value from the table, then that means we can conclude there is a linear correlation between shoe print length and height. Now, alternatively, we can use the p-value. Again, the p-value we can get from the results window from StatCrunch. So if you look back at the results window, the p-value is going to be 0.002. Where is it located in the results window? It's located right here. Okay, so there at the very end, 0.002. This is the p-value that we're going to use for our R interpretation. So because our p-value is less than our significance value, significance level alpha, so 0.002 is less than 0.05, that means we're inside the critical region. We can reject the null hypothesis, which we haven't really made because we're not hypothesis testing, but it comes out the same. We conclude shoe print length and height are linearly correlated. Notice whichever way you choose to go, you're going to get the same. You're going to get the same conclusion. Okay, so if you're given you have to be given a significance level, whichever way you go, and if you use the table, then you can get your critical value, compare it with the R. Otherwise, you're comparing the significance level with the p-value. Out comes your conclusion the same way either way. I want to mention really briefly the concept of explained variation. So if we square our linear correlation coefficient and get R squared, this value represents the proportion of variation in Y that's explained by the linear relationship between X and Y. This actually makes more sense when we get into some material in the next lecture about linear regression. So there's not much to understand about it now. But for now, let's just think about, we have found previously that our R value for our example for the shoe print length and height example is 0.847. So if we square that, we get 0.717. Okay. Now you don't have to use a calculator. You can use StatCrunch, that gives it to you too. So here in our output, okay, notice that the R square value is right here below where the R value is listed. So it's actually calculating that for you, which is nice. What this number means is that 71.7% of the variation in height can be explained by the linear relationship between lengths of shoe prints and heights. That's all you really need to understand at this point. So just kind of keep that in mind. Again, when we get into more of the material from the next lecture in regression, we can go into this more in depth and it'll make a little bit more sense. Common errors that are made. Okay, so when you're dealing with regression analysis, there's some common errors that are typically made. And the most common error by far is one of causation. Okay, so there are people who look at the results of these statistical tests and conclude wrongfully that, oh, well, look, we've got a really good R value. That means that, one variable is causing the other. Well, no, that's a logical fallacy. Just because there's a relationship between two variables doesn't mean that the relationship must be one of cause and effect. And again, correlation is simply saying there's an association between the two variables. It doesn't say anything about what that association is. So correlation never implies causality. Just because two variables occur together, well, that's all the correlation is saying. There's an association between that. When you see one, you tend to see the other. But that's not saying that one causes the other. That's a very, very different ballgame that you're playing when you make that conclusion. Another common error, averages. So it's very typical in the real world to have data sets with literally thousands of individual data points. How do you manage all of that data? Well, some people get the quote-unquote bright idea that, oh, well, it'd be easier to manage all this data if we just used averages for calculating our correlation coefficient. Well, that's not a really good idea. When you use an average, it suppresses the individual variation that you get by using individual values, and that can artificially inflate the value of R. So what you run the risk of doing is concluding that you have a correlation between your two variables when there isn't that strong of a correlation between them. So you always want to use individual values when you evaluate correlation and not averages. Another common error made, it relates to linearity. So some people, when they look at these tests and it comes out to say there's no linear correlation between them, they just give up and say the two variables are not related. And you don't want to do that, okay? Just because there's no linear relationship doesn't mean there's no other type of relationship. As we discussed earlier in this lecture, many real relationships by nature are nonlinear. So you want to go examine that. All this is saying to you, if you don't have a linear relationship, it says you don't want to look there. You want to look somewhere else. So then go look somewhere else. So if you don't find you don't have a linear relationship, just go look somewhere else. And this is one of the reasons why we make a scatter plot first thing out of the box, because the scatter plot often will tell us what direction we need to go in to look for a potential relationship between our variables, if there is even a relationship there at all. Again, if you get that shotgun effect, you're not gonna likely conclude that there's going to be a relationship between the two variables. I want to repeat this because you cannot overstate this. Correlation does not imply causality, okay? Apples and oranges are not the same thing. Yes, they are both fruit, okay? So, you may see a relationship between the number of apples and the number of oranges, okay? But that just means that the conditions that sponsor the growth of fruit are existing in both cases. That doesn't mean that, apples are causing oranges to grow or oranges are causing apples to grow. So just because there's a relationship between two variables does not mean that one is causing the other. I just cannot overemphasize that. So do not make the mistake of saying that one causes the other. Correlation means there's a relationship, nothing more. That's all it means. What the nature of that relationship is, well, you have to dig further into that to actually get that out. And we'll get into some of that later in the chapter. But the main important point that we want to keep in mind, correlation does not imply causality. I mentioned at the beginning of this lecture hypothesis testing, and yes, we can use the methods of hypothesis testing we've learned earlier to evaluate a claim that two variables are linearly correlated. So hypothesis testing can be one-tailed or two-tailed, as we know. In the case of hypothesis testing for linear correlation coefficients, if the claim is simply one of linear correlation, then the test will be two-tailed. But if we get more specific and say that the claim is positive linear correlation or negative linear correlation, then our test is one-tailed. We need to be aware of some notation that's typically used. So first, N is the number of pairs of sample data, as we've seen. R is the linear correlation coefficient for a sample of paired data. Okay, so the numbers that we're putting into that calculation for R, it's all sample data. So therefore, R is a sample statistic. The correlation population parameter is represented with the Greek letter rho. Why are we using the Greek letter rho? Well, again, many people, your authors, using the lowercase letter r to represent the linear correlation coefficient for the sample. Many people use a capital letter R for the same thing. So we can't be using capital letter R for the population because that's just going to get some people confused. So we're going to move to the Greek alphabet then, use the Greek letter rho. Hypothesis testing for linear correlation. We've got the same three requirements that we just went over previously for establishing linear correlation. Okay, so we need to make sure those requirements are met. Typically they are. Let's look first at two-tailed testing. So we form our hypothesis just as we've done previously. So the null hypothesis is going to be that our population parameter, which in this case is the population linear correlation coefficient rho, equals 0. Okay, it's a statement of equality, just as we've seen before. The alternative hypothesis will then be rho is not equal to 0. This is always the case for two-tailed testing, because remember, for two-tailed testing, the inequality sign for our alternative hypothesis will be not equal to. So, in effect, what our null hypothesis is saying is that there is no linear correlation. That is the null hypothesis. Okay? Remember this graphic that we saw earlier in the lecture. Okay? So, if our linear correlation coefficient is 0, that puts us smack dab in the middle of our range to where there's no correlation between our two variables. Okay? So that means that our alternative hypothesis is saying that there is a linear correlation. So if it's not 0, it's going to be some number between 0 and 1, or some number between 0 and -1. One tail on the left, one tail on the right. So two-tailed test. We can use the linear correlation coefficient R for our test statistic. And we can evaluate the test using the tabulated critical R values that we've seen previously. So if the absolute value of R is going to be greater than the critical value from the table, reject the null hypothesis, conclude there is sufficient evidence to support the claim of linear correlation. However, if the absolute value of R is less than or equal to that critical value from the table, we fail to reject H0, conclude there is not sufficient evidence to support the claim. If we want to look at a true test statistic, though, because the R value that we're using is really an approximation, the true test statistic is a t-score with n-2 degrees of freedom. So here's the equation for evaluating the true test statistic. Notice we're taking our linear correlation coefficient and dividing it by that minor monstrosity that you see there underneath the radical sign. This is our true test statistic. Okay. We then use this test statistic to find our p-value, which we can do by going to our t-distribution. So we plug in whatever our test statistic is, and out comes a certain area, and boom, there's our p-value. And then we can either use the test statistic or the p-value to evaluate the test, reject H0 if we're inside the critical region, fail to reject H0 if we are outside the critical region. Let's go back to the example we looked at previously, and let's actually go through the method of hypothesis testing with that example. So, because the claim is simply about linear correlation, we have a two-tailed test. Okay, remember, that's all the claim was saying. It didn't say anything about positive or negative linear correlation. It only said that they're linear correlated. So therefore, it's a two-tailed test. So, as always, we start by writing our hypotheses. And we start by expressing the claim symbolically. Okay, the claim is that our two variables are linearly correlated. So that could mean they're positively correlated or negatively correlated, which leads us to saying that rho is not equal to 0. The null hypothesis, by definition, is a statement of equality. So rho equals 0. The alternative hypothesis then generally reflects the claim. In this case, it exactly reflects the claim. And so we have a match between our claim and H1. Okay, notice that the not equal sign on H1 is indicating a two-tailed test, which is what we would expect. So now we go and use the test the claim. We've already looked at testing this with the R value. So let's go ahead and use the actual test statistic to test the claim. We can calculate this old school with the equation that we saw previously. substitute in the values we know, punch it out on our calculator, and out comes 4.503. Of course, we don't have to do that. StatCrunch can give us that. If we just go back to our results window that we had previously, okay, the test statistic is located right here next to the p-value. Notice it's the same number that we get with the old school calculation. This is our test statistic. Okay, now we can evaluate by comparing this test statistic with our critical value from the t-distribution. So going back to our t-distribution, we find our critical value is plus or minus 2.306. Comparing that with our test statistic, 4.5, okay, puts us well inside the right tail. Okay, that means we're inside the critical region, and because we're inside the critical region, we reject H naught and conclude there is sufficient evidence to support the claim that a linear correlation exists between shoe print length and height. The same conclusion that we reached earlier. We can also have a one-tailed hypothesis test. So tests don't have to be two-tailed, they can be one-tailed. And this usually happens when the claim is either that we have a positive linear correlation or a negative linear correlation. So here's a table that exemplifies what our hypotheses are going to be depending on if we have a left-tailed test or a right-tailed test. Notice that the inequality signs, as always, you can imagine them being an arrowhead pointing in the direction of our critical region. So left-tailed test has a less than sign, right-tailed test has a greater than sign for the alternative hypothesis. And then we just evaluate the hypothesis test using the linear correlation coefficient R with the critical value table, or we can take the p-value, compare it with the significance level, or we can take the test statistic and compare it with the critical value from the t-distribution. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class. Thanks for watching.